Titan, Saturn's largest moon, was once believed by scientists to be nothing more than a world of ice, rock, and silence. But when real images finally arrived, they shook the scientific community by revealing strange structures and mysterious flows that we still cannot explain. What is hiding beneath Titan's thick shell of ice? What flows through those river channels is not water, but liquid methane, a flammable fuel that is driving a weather system unlike anything ever seen before. Or the scenes that stunned scientists: landscapes resembling eroded riverbeds and smooth, rounded stones shaped as if they had been worn down by flowing currents over long periods of time. Even more striking, with an atmosphere denser than Earth's, continuous chemical reactions produce complex organic molecules, the fundamental building blocks of life. Prepare yourself for an unimaginable journey, and it begins right now. When scientists first observed Titan through telescopes from Earth, at a distance of nearly 1.4 billion kilometers from the Sun, where solar energy is less than 1% of what Earth receives, Titan should have been a frozen, barren world with a thin atmosphere or none at all. The data show that Titan possesses an atmosphere denser than Earth's. This is especially striking given that Titan has only about 1/40th of Earth's mass and a surface gravity of just around 14% of our planet's. The composition of Titan's atmosphere surprised scientists even more. About 95% is nitrogen, similar to Earth, but the remainder is not oxygen. Instead, methane makes up nearly 5%, along with a wide range of other hydrocarbons such as ethane, acetylene, propane, and cyanide compounds. There are also traces of carbon monoxide and carbon dioxide. Titan's surface temperature is around 94 Kelvin, equivalent to negative 179 degrees Celsius. Titan's atmosphere is not only dense, but also extremely deep. Due to low gravity and high atmospheric density, its layers extend more than 600 kilometers above the surface. The layered structure of Titan's atmosphere is extremely complex. The lower layers contain methane, where clouds form and rain falls. Above them are photochemical layers, where even faint ultraviolet light from the sun is sufficient to break apart methane molecules and trigger long chains of chemical reactions. Before Cassini, atmospheric models predicted that if Titan had an atmosphere, it would be simple and static, composed mainly of cold nitrogen. But reality proved entirely different. Titan has a dynamic climate system with convection, high-altitude winds, seasonal atmospheric circulation, and complex energy exchange between the surface and the atmosphere. How has Titan managed to retain this atmosphere for billions of years? Methane in the atmosphere is continuously destroyed by ultraviolet radiation and high-energy particles from Saturn's magnetosphere. On Titan, methane does not exist only in the air. It falls to the surface, forming rain, rivers, and seas, but not of water. On Titan, water cannot exist in liquid form. The surface temperature freezes water solid, as hard as rock. So what are these flowing channels? The answer completely reshapes how we understand planetary geology. They are liquid methane and ethane. Most of these lakes and seas are concentrated near the North Pole, where climate conditions allow methane to condense and persist over long periods. The most striking feature is Kraken Mare, the largest hydrocarbon sea on Titan, with an estimated area of about 400,000 square kilometers. Kraken Mare is even larger than Earth's Caspian Sea. Radar data and wave reflection analysis suggest its depth may exceed 300 meters in some regions. Nearby lie Ligeia Mare and Punga Mare, forming a connected system of seas that resembles miniature oceans in the polar region. Beyond seas, Titan also hosts smaller lakes and marshy regions, such as Huachuca Lacuna, which stretches nearly 449 kilometers. These lakes have well-defined shorelines and complex coastal shapes, indicating that liquid levels change over time. Some lakes have even been observed shrinking or refilling over cycles of just a few Earth years, pointing to a climate system that is actively operating. The liquids on Titan are not water, but liquid methane and ethane, sometimes mixed with dissolved nitrogen. At Titan's extremely low temperatures, methane plays a role similar to water on Earth. It evaporates, condenses, falls as rain, and flows across the surface. This process is commonly called the methane hydrological cycle. It begins when liquid methane on the surface evaporates into the atmosphere. At suitable altitudes, methane condenses into clouds. When the droplets grow large enough, they fall as rain, producing storms that can last for hours or even several Titan days. The methane then flows along the terrain, forming rivers and channels, eventually draining into lakes and seas, where it once again evaporates. One particularly striking feature is the uneven distribution of lakes and seas. The North Pole is rich in liquids, while the equatorial regions are relatively dry, dominated by vast hydrocarbon sand dunes. To understand why rain falls in one region and not another, we must look higher into the invisible motions within Titan's dense and dynamic atmosphere. If Titan's surface reveals a world shaped by rivers, lakes, and seas of methane, then the sky above is what controls the entire system. Every rainfall, every flow, and every accumulation of liquid begins with atmospheric motion, a complex mechanism that, before Cassini, humanity had never directly observed on any moon. Titan's atmosphere is so dense that sunlight is heavily scattered, creating a thick orange haze that blankets the surface. Data from Cassini and the Huygens lander show that Titan does not possess a static atmosphere at all. Cassini recorded methane clouds at multiple altitudes, and in some regions observed signs of fresh erosion, indicating that methane rain can trigger localized flash floods. One key factor that makes Titan's atmosphere so unusual is its long seasonal cycle. Titan's axial tilt causes sunlight to be distributed unevenly between the two hemispheres over time. When summer arrives in the northern hemisphere, solar energy increases enough to drive strong evaporation of methane from lakes and seas. Cassini observed methane clouds becoming more concentrated in the hemisphere entering summer, while the opposite hemisphere grew drier. This shows that methane migrates on a planetary scale, moving from one hemisphere to the other with the seasons. When the Huygens probe descended through Titan's atmosphere in 2005, it delivered rare, direct measurements of atmospheric structure. During its descent lasting more than 2 hours, Huygens recorded high-altitude winds reaching speeds of up to 120 kilometers per hour at elevations above 100 kilometers. The stark contrast between upper-level winds and near-surface conditions reveals a clearly layered atmosphere. In the upper layers, atmospheric behavior is governed by radiative energy and photochemical reactions. In the lower layers, it is strongly influenced by the surface itself, methane lakes, terrain, and local temperature variations. One important distinction is that clouds on Titan do not form continuously the way water clouds do on Earth. Titan demonstrates that climate is not simply a product of high temperatures or intense radiation, but the outcome of a dynamic balance between atmospheric physics and chemistry. And once we understand how methane clouds form, move, and dissipate within Titan's atmosphere, we begin to see that the surface Huygens touched down on, with its channels, plains, and dunes, is not random at all. When the Huygens probe touched down on Titan's surface on January 14, 2005, the first images sent back to Earth stunned the scientific community. What appeared before them was not an entirely alien world, but a surprisingly familiar landscape. Winding channels, sedimentary plains, rounded stones like river pebbles, and gently sloping terrain resembling dry stream beds on Earth. Panoramic images from Huygens showed that Titan's surface is covered by organic regolith, a mixture of solid water ice, organic tholin particles, and hydrocarbon sediment. The scattered rocks around the landing site are rounded in shape, ranging from a few centimeters to several tens of centimeters in size, suggesting they were rolled, collided, and eroded by flowing liquid. Spectral analysis indicates they are likely water ice coated with organic material, rather than silicate rock as on Earth. Titan hosts channels stretching hundreds of kilometers, with multiple branches forming river-like networks. Some of these channels flow directly into hydrocarbon lakes and seas, showing that they are part of a sediment transport cycle that is active or was active in the past. These are not static, ancient traces, but the products of geological processes that continue to operate in rhythm with Titan's climate cycles. Another prominent landform is hydrocarbon dunes, as Cassini discovered dune fields stretching thousands of kilometers near Titan's equator. These dunes are estimated to be 100 to 150 meters high, several kilometers long, and arranged in parallel rows like desert sand dunes on Earth. Beyond channels and dunes, Titan also has extensive depositional plains, broad, relatively smooth regions where sediment has accumulated over many methane rain cycles. One important observation is the scarcity of impact craters in many regions, suggesting that Titan's surface is relatively young geologically, or at least continuously renewed by erosion, deposition, and possibly internal processes. What makes Titan extraordinary is not simply that it resembles Earth, but the way it does so using entirely different materials. On Titan, methane replaces water, ice replaces rock, and organic chemistry plays the central role. Images of Titan's surface have forced scientists to revisit a fundamental question: what does a landscape need in order to form? And as we observe those cold, dry channels and endless organic dunes, a larger issue begins to emerge. Methane, the core element shaping this entire landscape, is not stable in Titan's atmosphere. Under the influence of ultraviolet radiation from the sun and high-energy particles within Saturn's magnetosphere, methane in Titan's atmosphere is continuously broken apart. This photochemical process converts methane into ethane, ethylene, hydrogen, and a wide range of more complex organic compounds. Photochemical models show that, at the current destruction rate, all of Titan's atmospheric methane would disappear in only about 10 to 50 million years. The first hypothesis is cryovolcanism, or cold volcanism, which is thought to release mixtures of liquid water, ammonia, and methane at much lower temperatures. Cassini identified several surface features suspected to be cryovolcanoes, such as Doom Mons and Sotra Patera, elevated regions with complex slopes resembling eruption centers. There are no clear flow patterns like lava, and measured heat output is low. This leaves cryovolcanism as a strong but not yet fully confirmed hypothesis. The second hypothesis involves methane clathrates, in which methane is trapped within a crystalline lattice of water ice. Under suitable pressure and temperature conditions, methane can be locked deep beneath Titan's surface. If this icy crust fractures, warms, or experiences strong disturbances, large amounts of methane could be released at once. A study published in 2025 proposed that major asteroid impacts in Titan's history may have played a key role. When a sufficiently large impact strikes the surface, the energy released can heat deep ice layers, break clathrate structures, and release methane stored for hundreds of millions of years. The third hypothesis looks deeper into Titan's interior gravity data and structural models, suggests that Titan may have a silicate rock layer in its core, in contact with liquid water in a subsurface ocean. In this environment, chemical reactions between rock and water similar to serpentinization on Earth can generate hydrogen, which then combines with carbon to form methane. Each hypothesis has strengths and weaknesses. Cryovolcanism explains unusual surface structures, but lacks clear thermal evidence. Clathrates can account for large methane reserves, but require a periodic triggering mechanism. It is possible that the truth does not lie in a single process. Titan may be drawing on multiple methane sources at once, operating across different timescales: slow seepage, sudden impact, triggered releases, and quiet production from the interior. What matters most is this: methane on Titan is not just an atmospheric component. Without methane, there would be no rain, no rivers, no seas, no erosion, and no familiar landscapes. But Titan is active, evolving, and shaped by a climate history. This shows that Titan has never been a completely frozen world. It continues to exchange material between its surface, atmosphere, and interior, a rare trait for an icy moon. And as methane is continuously destroyed and then reborn, an unavoidable consequence emerges: the accumulation of complex organic molecules. These byproducts of methane, created in the atmosphere and deposited onto the surface, have turned Titan into a vast chemical reservoir. This leads directly to the next question. If Titan has energy, a solvent, and such rich chemistry, could it be approaching the very first steps of prebiotic chemistry? If methane is the fuel that drives Titan, then organic chemistry is the deepest consequence of this world. Within Titan's dense, frigid, yet energy-rich atmosphere, chemical reactions never cease, hour after hour, day after day, across billions of years. And it is here that Titan reveals a trait that leaves scientists both astonished and cautious. It is one of the richest reservoirs of complex organic compounds in the solar system outside of Earth. The origin of all this begins in the upper layers of Titan's atmosphere, at altitudes of hundreds of kilometers, where ultraviolet sunlight and high-energy electrons from Saturn's magnetosphere can penetrate. Methane and nitrogen molecules are broken apart. This process, known as photochemistry, produces highly reactive free radicals. These molecular fragments rapidly recombine, forming ethane, ethylene, hydrogen cyanide, propane, and dozens of other compounds. According to data from Cassini and photochemical models, Titan may produce hundreds of thousands of tons of organic material each year in its atmosphere. As these molecules continue reacting and growing, they clump together into reddish-brown aerosol particles, forming the thick haze that blankets the entire moon. This is the origin of tholins, a term describing complex organic mixtures rather than a single molecule, but an entire family of chemical structures. These tholins slowly fall to the surface like an organic rain, lasting millions of years. What is striking is the chemical diversity of tholins. They contain carbon, hydrogen, nitrogen, and in some cases, even oxygen. Cassini directly detected several key molecules in Titan's atmosphere, including hydrogen cyanide, dicyanoacetylene, and benzene. HCN is particularly important because on early Earth, it is considered one of the fundamental building blocks for forming amino acids and nucleotides, the components of proteins and DNA. Some theoretical models suggest that in liquid hydrocarbon environments, molecules could self-organize into stable structures. Even hypothetical cell-like membranes known as azotosomes, nitrogen-based membranes proposed in 2015. If Titan truly has a liquid water ocean beneath an ice shell 55 to 80 kilometers thick, then throughout its history, large impacts or cryovolcanic activity may have created brief windows where surface organic material contacted liquid water below. It recreates many conditions similar to Earth more than 4 billion years ago. A nitrogen-rich atmosphere, radiation, driven energy sources, abundant carbon compounds, and long-term material cycling. NASA refers to Titan as a planet-scale natural laboratory, not because it is known to host life, but because it allows us to observe prebiotic chemistry in a pristine state, untouched by biology. On Earth, life erased much of its original chemical record. On Titan, those traces remain intact, slowly accumulating over time. With the Dragonfly mission scheduled to launch in 2028 and land in the 2030s, humanity will, for the first time, directly analyze organic material on Titan's surface. Dragonfly will fly across dune fields, collect samples, measure chemical composition, and search for patterns of organization, key indicators of prebiotic processes. The first clues came from subtle changes in Titan's gravitational field as Cassini passed by. Radio signals sent back to Earth were deflected by an extremely small amount. Gravitational models indicate that, to explain these observations, Titan must contain a liquid layer sandwiched between its rocky core and its outer ice shell. Cassini measured deformation amplitudes far greater than what would be expected from a solid icy moon. Such behavior can only occur if the ice shell is effectively floating atop a subsurface ocean. According to current models, this ocean lies approximately 55 to 80 kilometers beneath the surface. Above it is a thick shell of solid water ice. Below it stretches a liquid layer tens of kilometers deep, and deeper still lies a silicate rock core. Crucially, this ocean is not composed of pure water. It is believed to be rich in ammonia and salts, which lower the freezing point and allow liquid water to persist despite the surrounding extreme cold. Heat is generated by radioactive decay within the rocky core and by tidal friction as Titan is continuously stretched by Saturn's gravity. This same mechanism has been confirmed on Europa and Enceladus. But on Titan, the scale may be even larger. On Earth, an oxygen-rich atmosphere, liquid water covering nearly 71% of the surface, and an average temperature of about 288 K create conditions for life as we know it. On Titan, the atmosphere is about 1.6 times thicker than Earth's, yet it contains almost no free oxygen. Nitrogen is the dominant component, as on Earth, but the role of water is entirely replaced by methane and ethane. But when we look more closely, the comparison begins to reverse. Earth has a hydrological cycle. Water evaporates, forms clouds, falls as rain, flows back to the sea, and repeats. Titan also has a remarkably similar cycle, differing only in the liquid involved. Methane evaporates at extremely low temperatures, forms hydrocarbon clouds. rains onto the surface, flows through river channels, accumulates in lakes and seas, and then evaporates again. This is a complete climate system, operating steadily for millions, even billions of years. On Earth, landscapes are shaped by water and plate tectonics, while on Titan, images from Huygens reveal river channels, depositional plains, and dune fields stretching hundreds of kilometers. But the sand here is not silica. It is composed of complex organic particles bound together from tholins that fall out of the atmosphere. The greatest difference lies in how each world stores and distributes energy. Earth receives most of its energy from the sun, redistributed through the atmosphere and surface oceans. Titan receives very little sunlight, only about 1% of what Earth gets. Yet Titan still maintains an active climate thanks to its thick atmosphere, methane greenhouse effects, and internal energy from radioactive decay and tidal forces. This shows that a world does not need abundant sunlight to remain dynamic. When considering the potential for life, Earth becomes the only reference point we truly know. On Titan, the surface is inhospitable to Earth-like biology. Yet beneath the ice lies a subsurface ocean of liquid water rich in ammonia. There, water, energy, and materials may interact in ways entirely different from anything on Earth. What matters is that Titan does not violate the laws of physics. Instead, it exposes the limits of traditional planetary models built from our single example, Earth. Real images from Titan have completely overturned the idea of a quiet, inert, icy moon. Instead, we are confronted with a complex, dynamic system, where the laws of nature appear to be rewritten in an entirely different chemical language. Continuously evolving landscapes and unusual chemical signals beneath Titan's characteristic orange haze point to an internal energy source or a quietly unfolding prebiotic process. This presents a profound challenge. Titan is not merely an object to be observed, but an active world that directly questions the limits of modern scientific understanding of life. Titan stands as proof that the universe is always more complex than we imagine, and that unraveling the nature of this moon may ultimately be a key to understanding our own origins. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.